Just the announcements to remind you about install WMS, because we'll start using it in class on Monday after spring break, and please bring your computer. You'll really have an ineffective and unpleasant time over the coming weeks if you don't have some way to participate. So please bring WMS installed starting Monday after spring break. Homework 8 is due that same day, Monday the 21st. Now today we're going to continue looking at this preview of WMS, but before we do, I thought we'd spend some time doing a conceptual review just to remind you that our exams have concept questions, and during the first exam that seemed to be what some people struggled on. So before we do that brief concept review, any questions about the announcements or course stuff in general? All right. So I promised you that there'd be at least 30% of the points on the next midterm exam would be from conceptual questions. It'll probably be about a third. And so if you look over the concepts that we've covered since the first midterm exam, it's largely been related to watershed modeling fundamentals. And so the first question that I might ask could be related to unit hydrographs. And I probably wouldn't make the question be as open-ended as how does a unit hydrograph work, because that would be a long answer. I'd try and focus it a bit more than that. But since we're just talking verbally and you're not having to write your answer by hand in a timed exam scenario, maybe this is okay. So who feels like they could take a stab at describing a unit hydrograph and how it works? And I guess basically what I mean by how does it work is, number one, what is the need? Like, why do we have unit hydrographs? How is a unit hydrograph developed? And then how is it applied? So let me write that on the board. The why, number two, would be how developed. And number three, how do we apply a unit hydrograph? So first of all, the purpose of a unit hydrograph. And anybody want to take a stab at what's the motivation for having and applying a unit hydrograph?
So we can see how a given watershed will react in terms of runoff to a given unit of rain.
Perfect. Really good. Thank you, Seth. That's great. So we have a hydrograph, and it's got streams. We have a watershed with streams. And what the unit hydrograph method does is we say we want rain to go over this watershed, and we want to predict the runoff. And so it's one of the most simple ways of connecting that relationship between the rain comes from the sky, what's coming out of the stream. All right, so good. We know about the why. That's why we do it. Now, what about how do you develop the unit hydrograph? Where does it come from when it's being generated?
There's a couple factors. One is how much runoff there is, actually, like how much rain there is, the like the slope of it, and then something probably with the soil, which has to do with the amount of infiltration and runoff. Okay, good. So there are a lot of factors that influence what that unit hydrograph looks like. Logan mentioned the soil characteristics, the slope, the rainfall characteristics. So there's a lot of things that influence that. To actually generate a unit hydrograph, you have to have instrumentation in the field. And so the things that you'd need to have would be a rain gauge and a stream gauge. Because when the unit hydrograph is first prepared, it's a physical measurement of rainfall and runoff. And then once you have that for a watershed, you can transform it by having different rainfall depths, different rainfall durations, and then you can, maybe you're on a little bit thinner ice when you apply that unit hydrograph to other watersheds that have a different size, different slope characteristics. But the starting point, how you develop it, is instruments in the field that measure the rainfall and that measure the stream flow. And they have to be synchronized. They have to have the same kind of clock, because one of the things we want to know about is the timing.
It's not just the amounts. And so in part, we want to know what depth of rainfall leads to what peak runoff. But then it's also the lag time between the rainfall and the runoff that's really important. So they're measurements of amount versus time with a common time basis, because there will be a storm event, and when that storm event begins, so does our timing for the runoff. All right, so that's a little bit about how the unit hydrograph is developed. Now, what about how do we apply the unit hydrograph? Anything else to say that hasn't been covered already about how it's applied? If you're going to try and show on an exam that you really understand this concept and deserve a heap of points, some of the things that you might say just to really show off about how much you know is you could talk about what technique is used to change the storm duration. Or remember that a unit hydrograph is, let me just draw this on the board. We've got this representation, which I'm cross-hatching, and then is this. Okay. So let me point to this part of the figure that I've just drawn on the whiteboard. What does that represent?
The time it takes for the water to start to run off.
That's a good guess, but that's not this particular component of it. This part is the hydrograph. Yeah. So who said that? Okay, so you said the hydrograph. Right, so this is the rainfall. The width of it is the duration of the rainfall, and then how long it is the depth. So maybe we're saying that this is 1 inch, and I got to be careful here. I want to be precise. That's not an inch of rainfall, that's an inch of rainfall excess. So 1 inch of rainfall excess causes this runoff. So on this discussion of how you apply a rainfall, a unit hydrograph, what do you do if, let's say this was 1 hour of duration? What if you have a storm that's 3 hours long? Do you remember what you did on the homework?
Don't you use the S-curve?
S-curve is to change the storm duration. What I was thinking of is how you have you skip a row for the next hour, the subsequent delays. Let me see if I've saved that. Stagger it. Exactly right. Unit hydrograph example. So let me illustrate what we did previously when we had successive pulses of rainfall. Yeah, I'm glad I did save that. Okay, so in this example we had during one period 0.9 inches of rainfall excess, then 1.5, then 0.7. And what these were is it was this intensity for 2 hourly periods. And so hour 1 and hour 2, we're both seeing this rainfall hydrograph scaled from so it's 0.9 times that. So that's why we see 3.6, then 9 instead of 10. But then for the second hour, it's staggered 1 hour later. And then during the third hour, you can see we're just adding an extra leading 0 to the rows. And so, how to apply if you have longer than the duration of the storm is successive repeats of it. All right, so hopefully that refreshes your memory a little bit about unit hydrographs. Now, next question, what does the NRCS method do? So I guess we could follow maybe the same process of number 1, briefly address why, like what is the purpose of the NRCS method, like what is it attempting to predict, and with what input data, like what's the input to the NRCS method and what's the output from the NRCS method. And then let's talk about like how did they develop it, and that's kind of related to what's going in and what's going out. And finally, how it's applied. This is all kind of combined together in the case of the NRCS method. So who wants to take a stab? Who's feeling brave? NRCS, by the way, stands for National Resource Conservation Service. and that is that's a sub-office in the federal government that's part of the Department of Agriculture. So NRCS, National Resource Conservation Service. All right, NRCS method. Why do we have it?
It predicts rainfall excess and it accounts for storage, retention, the rainfall in, and you can also calculate IA.
Good. All right. So you said that it's predicting rainfall excess. That's what comes out of the method. And what goes into the method is factors that describe storage, you mentioned, right? And so what is the chief input for defining the storage? Do you remember in that formula for S, which is storage, curve number, right? So curve number. What else goes in?
Use a precipitation value.
Precipitation, right. And that's more or less it, since we assume that the initial abstraction is a function of, like, it's 20% of the storage, and storage is based on curve number. So really that's all that's going into the NRCS method. But curve numbers, of course, there's a lot of factors that dictate what the curve number is in the NRCS method. So let's talk about that here in part 2. How is the curve number developed? Like, what are some of the things that curve number is meant to reflect?
Infiltration, infiltration and runoff in a designated area based on the soil and the ground surface.
Okay. Good. So infiltration, what is that specifically? I sometimes talk about two things in particular that directly impact the curve number. Infiltration is related to what?
Was it the soil, like the ABCD?
Yes, soil. So infiltration is related to the soil, and we've got the hydrologic soil group. Hydrologic soil group, which is A, B, C. And so part of the way that they classify A, B, C, D is the rate of infiltration. Okay, so there's soil group. What else?
Antecedent moisture condition.
Okay, antecedent moisture condition. Very good. What about when we're comparing concrete to grass? Do you remember what that's called, that category of data? Land use. It's land use. So the land use and the soil type together are the main factors that determines the curve number. And so other things that are built into that include like the slope, the quality of the vegetation. You know, some of the tables we've looked at have had good grass or poor grass. And that's talking about the coverage, you know, how much of it is bare earth versus how much of it is grass. Different curve numbers for different slope of the ground and so on. All right, and then finally, how do we apply the NRCS method? Well, we apply it by looking at a watershed, finding out what are its land use characteristics, what is the soil type in that watershed. We obtain precipitation data for the watershed for a certain return period that we're interested in. And then we, with the NRCS model, are then able to predict what would be the rainfall excess for a storm of a certain depth. So if there's precipitation 3 inches, how much is going to come out of this watershed in terms of the rainfall excess? And of course, that depth multiplied by the area of the watershed then gives you a volume of runoff. And then we use the unit hydrograph to tell us about the timing. Because what comes out of the NRCS method is just the depth, inches or centimeters. But if we want to turn it into a flow rate, we need some sort of a translation tool that turns depth into flow rate. And that's what the unit hydrograph does. All right. Any questions or discussion before we move on to one more of these? the S-curve method. Somebody mentioned that earlier, the S-curve method. So let me draw a hint. But what is the S-curve method related to? It's the same figure I've already drawn today, where we've got one of these and one of these. All right, so a hydrograph and a hydrograph. So what's the purpose of the S-curve method? Does anybody recall what we were trying to do with that?
S-curve method was for like changing the duration of the storm.
Exactly, yeah. So let's just say that you had a unit hydrograph with a hydrograph component of half an hour. If you wanted to take the unit hydrograph that you already have and use it for a storm of a different duration, then the S-curve method is what you'd use to make that new one. So you know how I said you make an S-curve, you make a unit hydrograph with two instruments being out in the field, like two sensors or devices. What are the two sensors that you have to generate a unit hydrograph?
Runoff excess and rainfall.
You'd have to have a measure of the rainfall and then some sort of a flow gauge. So it could be something that tells you the depth of the water. It could be a velocity meter that's telling you, when there's a certain depth, what speed the water's going. There's a variety of ways you can say, like, what's the flow rate at a location. So you've had physical measurements. So if you have a bunch of storms, none of them is probably going to be exactly 1 hour. So most unit hydrographs will have had the S-curve method done to them to translate all of that observed storm durations into like a 1 hour storm. And then they take the average of 5 or 6 of those and come up with the overall unit hydrograph that's typical for that watershed. So the purpose of the S-curve method, I guess I was going to type out my answer. I'd say the purpose of the S-curve method is to adjust the duration of the storm used to produce a unit hydrograph. So it's all about the width of that hydrograph that generates the unit hydrograph. All right, so there's more of these concepts out there for you to know and master, and you'll get your chance to prove that mastery in our next exam. All right, well, let's take a little bit of time to look at using WMS for the rational method and for the national streamflow statistics. Those are, national streamflow statistics in particular is one that you just learned about for the first time, I think, on Monday's class when we were talking about how there's this series of regression equations where they tell you what the peak flow rate will be based on the drainage area. So what I'm going to do is go through this wizard. You maybe remember the wizard hat from last time and how that steps you through the workflow, the step-by-step process that's needed to identify and delineate a watershed. And sometimes what I do is first locate the project site on Google Maps, because you get an idea of like the shape of the roads in that area and the shape of the stream. And sometimes the trickiest part is just finding like which stream crossing are you even actually talking about. And so just to give you a hypothetical, let's say that someone is telling you that the bridge is constantly underwater at a certain part here of Huntington. So let's go to Huntington, and you know that stream that goes through Ritter Park?
Mm-hmm.
All right, Four Pole Creek. Let's delineate the, they're working on the bridge at 5th Street right now. They've been doing construction there, it seems like forever. But let's delineate like how much watershed is contributing to the stream as it crosses under 5th Street. All right, so what I'm going to do is start up the wizard here, and we have to first save the project because WMS is likely to crash when you least expect it. It's great software, but much of it is coded by students, believe it or not. So you never know when it'll crash. All right. We'll save this, and right now it says that it's untitled, and it's not until you click save that actually creates that surrogate. And there will be more than just that one file eventually. Right now it might just be that one, but as we download the land use and soil type, it'll also put those files in that same directory. And you need them all to be able to open up the model again. All right, so then this part is I've got a projection defined. We're in West Virginia, so zone 17. I'll show you a map of which zones are in which regions, like which states and so on. Just a lot of the data that's available for us to download, the land use and the soil type, will be in this UTM, Universal Transmercator. It's just, you know, the Earth has an interesting shape that's not completely circular or spherical, I guess. And so there's different ways of accounting for the shape of the Earth's surface and how to create a coordinate system over that curved surface, and UTM is one of those. Okay, so here in the project boundary, I'm going to type in Huntington, West Virginia, and it's done it before. There we go. All right, so here's the thing, is I don't know exactly at first how big the watershed is. So I don't know, like, should I be zoomed out this much? Probably that's too much. And if I zoom out that much, it's going to take forever to get all the data. So, and to process the data too. So just downloading the data is the tip of the iceberg. So if I just have it zoomed in on the park itself, well, that's also a problem, because, you know, here's that crossing. Here's 5th Avenue and Four Pole Creek. But, I mean, if the creek goes off the screen, then you haven't got the whole watershed area. So it's sometimes an iterative process of guessing. And you can kind of see some of these boundaries, but this is a big watershed. I've delineated it before. So maybe as a starting point, I'll have like this much of it in view. And then if we have to zoom out even more, you'll see why. So I'm going to click this as our starting point, and you'll see what are the indicators maybe that we have either zoomed out too far or not zoomed out enough. Okay, so I'm going to use the web services, and then just as the first thing I want it to get is the elevation data. I won't yet get the soil type or the land use until I know that I've got the right watershed boundaries, zoom out versus zoom in. Okay, so I'm going to just tell it here the worldwide elevation data. So that's checked, but none of the other ones are. I'll click download data from web, and it's going to give me the chance to tell it whether I want to resample the elevation data. So the elevation data, as I think I hinted at last time, it takes this window that we've selected and it breaks it up into smaller pieces. And so right now what it's suggesting is it's saying 30 meter by 30 meter is a good blend of how long it's going to take to download, how big the file will be, but there's more resolution available if you want it. Like West Virginia has some of the highest resolution elevation data in the entire United States. I think the entire state has LiDAR coverage that's accurate to really maybe centimeter scale in terms of the vertical differences, and then horizontal, I don't remember exactly what the precision is, but it's a lot more accurate than 30 meter by 30 meter mesh. But this will probably be good enough for our purposes because there's so much elevation difference in our watershed. You need more resolution the more flat things are to try and be able to differentiate the ridge lines. But here, since it's so hilly, you can get away with a 30 by 30 meter cell size and it'll be fine. So I'll just click OK, and you'll see how quickly that downloads. It's doing it now, and there it is. Okay. Over here on the left side, it's shaded things in a colored way, just you know, the heat map where blue represents the, I guess I don't understand why it has these numbers here, because red is higher elevation, but yet it's got the lower numbers. You see, this is the flat part of town. We know that Huntington is the flat part, but yet it's got the blue colors, and then these numbers are reversed. That's maybe something I'll have to check with the Aquaveo people on. But that won't, I mean, I think that's just maybe they've got the scale reversed or something. Here you can see the flat part of Huntington, the hills, and so on. Let me turn off the elevation TIFF. All right, now it's tricky to know exactly my location, so I can turn on the map of road data. So that's up at the top here, get data from map. I'll...
Dr. Wade?
Mm-hmm.
Do you think that the scale is like for those lines rather than where it was colored in a minute ago?
Oh, yeah. It makes more sense now, doesn't it? Because the red is the low elevations here, and the green is the higher elevations. So you're saying it's not these colors, it's the other ones, right?
Right.
Yeah, I think you're right. Yeah, good call. So when it was showing both simultaneously, then that was confusing, but I think now it makes sense that the red is the low points. Odd that they would have the temperature flipped on this one, where it was blue is low elevation. All right, we've solved the mystery. Seth solved the mystery. Okay, let's turn on the map data in the background so we can find that crossing location again. So I'm going to get online maps and turn on the World Street Map so we can zoom in on the park. And it takes a minute for it to stream because it's going to download that on the fly. Okay, so it is here. North Boulevard. It's blurry now. Okay, now it's all right. So it's not yet showing the stream just in the elevation data because we need to do the Topaz. So I can turn this off temporarily, the street map. I'm going to go back into the wizard, and you remember last time, what Topaz does is it calculates the flow direction for every cell. So the way it does that is, remember, we've basically got a grid of elevation. And what WMS is doing is it's saying that in this cell, which is 30 by 30, it assumes that the elevation is the same everywhere there. So there's a 30 by 30 meter cell that has one elevation. But then it's going to look at the cells that are next to it. So for this cell, for example, it's going to look at what has the lowest elevation in the surrounding cells, and then it's going to assume whatever has the lowest elevation, the flow would go towards that. And it'll do the same thing here, for example. It'll compare it to all of the surrounding cells, and then it'll determine a flow direction by whatever is the lowest elevation in the adjacent cells. And so it does that for every cell in here, and then it determines the flow paths by looking at these directional indicators. Okay, so when I click on Compute Topaz, it's doing that process of comparing elevations to adjacent ones and finding the flow direction. Okay, so it started and it finished. It's very fast. But what it does now is it predicts where the streams will form. And here, right now, I have it so that anytime you've got at least half a mile of upstream area, then it's in blue. If I change it over to 0.2 square miles, then it's going to reduce how long those are. And now you'd have to have at least 0.2 of a square mile of upstream area before it shows where the stream is forming. So one way to think about it is, like on a dry day, maybe you'd only see streams at these locations, but then when it's raining, remember how the portions of the ephemeral streams that are usually dry become full. So on a rainy day, the location in the watershed that you actually see flow extends deeper into the network. All right, so what we need to do is zoom in on our crossing location. Let me turn on the street map again. All right, so we're looking here at the intersection of 5th Avenue and North Boulevard. So here is Four Pole Creek.
Yeah.
And it doesn't exactly line up with what the map is saying. You see how there's some differences there? I mean, the shape of it is similar, but why do you suppose it's not exactly in the right spot? Maybe it's hard to see because it's, let me turn some of these things off. Let me turn off the elevation contours. Oh, if we turn that off, then we lose the blue lines. Okay, so it's showing, like, here is Four Pole Creek. Part of the problem why it's not exactly in the right location is this 30-meter thing. You know, like, each one of these blocks is 30 meters by 30 meters. But, I mean, it broadly lines up. Like, you can see from the shape of the road that it's curving, and so here's the stream. What we want to do is specify the outlet location as right here, just before this branch, because this branch is catching all of the water that would enter the stream from this watershed that Fifth Avenue follows. So just prior to that would be the flow that's going to go under the bridge. Okay, so let me go over here, and we're going to create an outlet point, and this is where you're saying, I want to know right there, where I've just clicked, what is the contributing area to the watershed at that point. So I click on Delineate Watershed, and let's see if I've zoomed out far enough or too far. Okay. We've got most of the watershed, but not all of it. And the telltale sign that I didn't zoom out far enough is, you see this flat line across the bottom? No watershed is going to have a boundary like that, which is perfectly horizontal and flat. Like, look at how irregular it is. It's irregular, and then down here at the bottom, it's just happens to be perfectly flat there and there and there. It's just obvious I didn't zoom out far enough. So unfortunately, what it means is that we have to start this process over again, kind of from scratch. The one thing that we've got preserved is, like, if I don't necessarily have to zoom out. If I just panned the whole thing a little bit, then that would maybe get enough of it. So see how it says the area right now is 12.68 miles? 12.68 miles squared. That's most of it. I'm guessing that we may not even get to 13 square miles. But let me click this, New. It's just easier just to throw everything away that we've done so far. So New, no, we don't want to save the changes. Start the wizard again. I can just call it the same thing and overwrite my previous file, because the previous file didn't really have anything that valuable. Now define the project bounds, and it remembers my previous location. So what I'm going to do, rather than, if I zoom out even more, it's going to give me so much data. I think I can get away with just doing this, panning a little bit, because my watershed doesn't go that much into the flat part of Huntington. So I just panned a little bit, and that might be good enough. One of the things is this vanishes into the background occasionally, and if you like click on the icon, it'll bring it back to the forward. The little wizard window sometimes falls behind the WMS window. All right, so now let me go ahead and get that elevation data again. Worldwide elevation data, download it. Now it's suggesting 60 meters. No, I want to get the 30-meter data. In fact, let me go whole hog here. I'm going to get the 3.7 meter resolution data. It'll take a longer to download, and Topaz will take longer, but it'll be all right. So it's downloading it, and look at the download speed here down at the bottom. 4%, 5%, 6%, 7%. Maybe I should have done...
I was just going to ask, so you noted, like, whenever it generated the streams, it was off by a little bit?
Yeah.
Is there any use of, say, break lines or something like that, or a way to define a region that you'd like to look at more with a higher resolution?
No, the whole grid will have the same resolution. So, like, if you notice that it's different, different from reality in a significant and problematic way, your only solution is to just pick a higher resolution DEM. So it'll be interesting now that we've done that. Let's see if it more closely follows where we know the stream location actually is. I'm regretting it's going to take forever to run Topaz on this. I wonder if I can cancel it along the way. No? All right, well, we're 2/3 of the way done. Yeah, that's a great question, though, because if you could just be selective about it, like most of the watershed, probably that 30-meter resolution would be fine, but in the flat part of the city is where we really need more density of points. Unfortunately, that's not possible. All right, almost done getting this elevation data, and then we'll see how quick it can get through Topaz. I didn't think I had zoomed out, so I'm surprised that it suggested the 60-meter resolution, because it was just the same zoom-in level but panned upwards. So we're beginning to see the effects of having that greater point density. The computer is struggling to load the points. Not responding. That's a bad sign. All right, I'm going to close the program. Luckily, it'll remember the location, so I'll just download the same location, but yeah, maybe the 15 instead of the 3.7. Define project bounds. All right, so we're still in this spot. And when I go to the web catalog, instead of the 60, I'll do 15. This should go faster.
Yeah.
Okay, so we downloaded it, and it's displaying it. All right, we're good. Compute Topaz, and it'll show me those streams. It starts. It's taking longer than Topaz took last time. Still thinking. Termination. All right, we're good. So I'm going to turn off the color mapping. And yeah, there's more precision. Okay, so let me turn on the road map so that we can find the intersection of 5th Avenue and North Boulevard. It's here. It's more closely following the stream location now.
I think it's funny that they have streams in the middle of the roads there.
Yeah. I mean, it's close.
I mean, I guess that's how Huntington works.
Oh yeah, like the street in front of my house is an ephemeral stream.
Yeah. All right, so let me drop the outlet to tell it at what point we want to delineate the watershed. And then, yeah, oh, by the way, you really want to get it on that blue line, because if it's in the wrong spot, then it won't delineate. So you have to make sure that you click in the right on the flow accumulation cell. I hope I got it. It looks like I might be a bit low. So it's calculating all of the things like the maximum flow length within the watershed. You can see at the bottom it's giving us the update on calculating the maximum flow distance, because what it's doing is it's calculating every possible flow path. All right, so this time we got the whole watershed. So you see how there's not that flat line that we saw before? And it's suggesting that the area of the watershed is 13.60. 13.60 miles. So as long as you've got like a little bit of contour lines on every side of it, then you can feel confident that you've got the whole watershed delineated. Okay, so then how would we do the rational method with this? We can go into the hydrologic modeling wizard, and even if we don't have the curve number defined yet, we could still use the rational method. let's see. If you double click on here, then it will tell you right now we're set to do the HEC1 model, which is one that uses the NRCS. So in the drop-down box here is where you can choose whether you're using HEC1, National Streamflow Statistics, rational method. So let's just see how it would deal with the rational method. It wants to know the rational coefficient for this watershed, which is way too big. Normally we'd only use the rational method for a watershed that's around 80 acres or less. This is much, much bigger than that. But just to show you how it calculates, if this had a runoff coefficient of 0.6 and we had a rainfall intensity of 3.5 inches per hour, it's already calculated the area for us. So it filled in the area based on the calculations that it did. And then it has a tool that you could use to calculate the time of concentration. Okay. Let me bring this back up. So if you use the Basin data, then it has a bunch of different methods. Some of these may be in your memory, like Kerpich, Kirby. I like to use the SCS method for calculating the lag time. It requires you to know the curve number, which we don't yet have, but a typical curve number in basins like this would be 68 in West Virginia. So once it knows like the length of the watershed, the average slope, the curve number, then it can calculate the lag time for you. Here it's saying 2 hours is the lag time, so it uses that to then calculate the time of concentration, and then the flow rate it's predicting, 18,426 CFS for this large watershed if we had a rainfall intensity of 3.5 inches per hour, which is a pretty high intensity. Now remember, we're outside the range that would be typical for a watershed to be using the rational method, but instead of the rational method, what if instead we used National Streamflow Statistics? Now we're going to get a much better, I'm just going to double click down here on the watershed and it'll pop open the window for National Streamflow Statistics. We're not in Alabama, we are here in West Virginia, so we have to remember that there's different regions, and the region that we are in is the Western Plateau. So I want to know the peak flow of the Western Plateau region, and then you basically already it's putting in the drainage area in square miles, 13.6, and you click compute, and then it's estimating what would be the runoff flow rate for the 2-year storm, the 5-year storm, the 10-year storm. So it's saying, for example, the 10-year storm is going to have a flow rate of 1,800 CFS. The 25-year storm, 2,300 CFS. And remember that the assumptions of the National Streamflow Statistics is that this is a rural, unregulated watershed, so that there aren't any dams or hydraulic structures regulating the flow in this watershed. So that's what you've got to look forward to in the week after spring break. Is we're going to get in this habit of being able to, I'll tell you a location and you'll delineate the watershed for that location. So it'll maybe be some site where they're putting in a culvert or where a bridge is being replaced, and what we're trying to do is assess what's the flow rate here at this location that comes from the watershed that's upstream. So you'll get really well practiced in the method of dropping the location on the map, having the appropriate zoom level to ensure you've got all of the contour lines you need to delineate the watershed, and then putting it into one of these models that will predict the flow rate versus time. That's it. It's 12:49. Thanks for being here on the day before spring break. I hope that you all travel safe. And remember that last look at these announcements. What you've got on your plate is homework number 8, which is due the day you come home from spring break. All right, that's it.